All right, so let's get into 12.1 more specifically. We're going to cover two different inference procedures for linear regression: confidence intervals and hypothesis tests. So first, describe the strength of the relationship between x and y. Just the strength here, direction and strength. So I would say this is positive, and I'd say strong. This one I'd say is positive and weak. And this one I'd say, I'd probably say maybe a little negative or maybe no association at all. So the idea here is, if we're taking a census, then we know the relationship we see is truly positive and weak, or no association. The problem is, though, if we're sampling from a population and we see something like this, can we really say the relationship in the population is positive and weak also? Or might we have just gotten these 20 points and the population has got a whole lot more points and the population is actually negative? So a question of interest becomes, when we sample from a population, if we see what we see in our sample scatter plot, what conclusions can we draw? What inferences can we make about the population scatter plot when we don't have the population data? So I think that's kind of what I was talking about right here. The question is, does our sample give enough evidence of an association between x and y in the population of interest? That's the question of interest. We can't run a chi-squared test for independence to see if there's an association because data is not categorical. You know, it sounds like chi-squared test for association is the one that we're always going to run. Well, if the data is categorical, sure. But if it's not categorical, if it's numerical, and bivariate, by the way, bivariate meaning we have two variables that we're seeing the relationship between, then we got to do something else. Well, this was last chapter. This is this chapter. So here's some notations: x bar mu, population parameter, population proportion. Sample proportion, population proportion, sample parameter. So proportion, population is to a parameter, as the sample things are to statistics. I completely said that incorrect, or I don't know, I was mixing up my words here, but so these are all statistics because these are all sample measures. These are all parameters because they're population measures. So sigma and S, Greek and normal. And then for slopes, we're going to introduce beta for the population parameter slope and B for the sample statistic slope. If there's a positive association between two variables, then our population slope is going to be greater than 0. If there's a negative relationship, then it's going to be less than 0. And if there's no association, then beta is going to be equal to 0. So these are the three things we're interested in figuring out. The sampling distribution of B. So we saw this in a previous slide. We kind of did this partial sampling distribution of 500 samples from the California schools model. And we can see kind of what the sampling distribution looks like. So we're going to learn some conditions, the conditions for our inference procedure. We're going a little bit backwards here, but when the conditions are satisfied, then this is going to describe the shape of our sampling distribution of sample slopes. The shape's going to be approximately normal. The mean of my sample means is going to be the true population slope. The mean of my sample slopes is going to be equal to the true population slope. This tells us that B is an unbiased estimator for the population slope, beta. And this is going to be the standard deviation of my sampling distribution. The standard deviation of my sample slopes is going to be sigma, which is the standard deviation of the residuals for the entire population, divided by the standard deviation of the x's for the census data, times the square root of n. So this formula is not on your formula sheet, and to be honest, you really don't need to have it memorized either. You'll never need to use it for a test. So I'm just giving it to you here kind of as a FYI. Standard error of the sample slopes. So when we don't have census data, we obviously don't know these population parameters. So we're going to use sample estimates. So we'll use S sub E, which is our standard error of or the standard deviation of our residuals. We'll use the sample standard deviation of X, and we are going to multiply by the square root of n minus 1. Some kind of degrees of freedom argument there, right? So this is really the formula we're going to use. However, it is also not on your formula sheet, and therefore not something you necessarily need to know. Conditions. Big star by the conditions. This you need to know. There are 5 conditions. I kind of think of independence as a 2-part condition, so I kind of maybe even think there might be 6. And we use this liner to help us remember them. L-I-N-E-R. We're doing linear regression, so I guess just forget about the A. So the first condition is that you have a linear data relationship. So the actual relationship between X and Y has got to be linear. Yeah, this is a little heavy, this one right here. For any fixed value of X, the mean response, mu sub Y, falls on the population true regression line. What that's basically it's basically a check for linearity. If this highlighted portion fails, then you don't have a linear model. Your data doesn't follow a linear model. Independence, the individual observations are independent of each other. We'll call that check 1. And then because we're sampling without replacement, you also check the 10% condition. So kind of a 2-part check there. And for normal, for any fixed value of X, the response variable varies according to a normal distribution. So what this is saying is that if I have my little scatter plot here, and I have the line of best fit, this is saying for every possible value of X in my input, my responses need to be approximately normally distributed about the least squares regression line. Now I don't have any data points there to see if this is true. Here I have one data point. So for that value of X, I need to have a nice normal distribution. So you can see maybe how difficult this check is to come to terms with. For every value of X, we have to have these normal curves about the least squares regression line. We don't have anywhere near enough data points to test it for even one value of X, much less for an infinite number of values of X. So we're going to have to figure out how to check this one here down the road. And by the way, this one right here, this one is saying for every value of X, the mean of these X's, the center of this normal distribution, falls right on the least squares regression line. And the mean for this one falls right on the least squares regression line. That's what's going to make it linear, if those means are in the right spot. Equal standard deviation. So not only do these have to be centered on the line and have to be normal, but they have to have equal standard deviations also. So you can't have one value in here that's super spread out and then others where it's close. All of these normal distributions have to be approximately equal in variability. And then the last one is our good old random check. All right, so we got some pretty complex ideas here. How do we actually check them? All right, so for linear, just check the original scatter plot or the residual plot, just to see if the relationship is linear. If you're looking at a residual plot, just say, yeah, we got random scatter, so it passes so it's linear. If you see a pattern, the check would fail. So pass, fail. Independence. Check 2 parts. First part is just saying each observation is independent of the other observations, and then the 10% condition. That is not really anything new. normal. Because we don't have enough points to see normality for every single value of x, we are going to collapse those. What we're going to do is we're going to drop all of these points down and make a dot plot of our residuals to see if the residuals are approximately symmetric. So just look at the distribution of the sample residuals. This is a residual plot. X versus your residual. These are dot plots of residuals. So it's a one variable plot. I'm just looking to see if these things are approximately symmetric with no outliers. Now you might look at it and say, well, it looks like it's approximately normal, but remember, don't ever say sample data is approximately normal, or I guess approximately might be okay. But if you have a small data set, that's not going to cut it. Just say it's symmetric, it's not strongly skewed, and there's no outliers. Over here, if your residuals look like this, we would fail to check because I have strong skewness in my residual list. By the way, what would this look like if you were to make a scatter plot? There's our line of best fit. I have a whole bunch of residuals that are relatively close to the line of best fit and nothing further than 6 away. But on the upper side, my residuals are very much spread out. What's going to happen when you get this is if you take this cross-sectional area, these are not normally distributed about the line. You see how they're skewed to the right, skewed to the positive values? So that's why checking this helps us see if these are kind of symmetrically distributed about the line. Okay? Equal standard deviation. This is what we want to see. This is the line of best fit. I want my values, my data points, to be kind of equally spread about the line for all values of x. So this is what it looks like here. This is what it looks like in a residual plot. Kind of equal spread about the line. Not this is what it would look like to fail. So for small heights, for some reason my predictions are really good, and for large heights, for some reason my predictions are really much more spread out. Or not my predictions, but the actual values are much more spread out. Yeah, so this would be a failing. Basically, you kind of see this fanning of more variability for different values of x. And then random check. Samples got to be random or randomly assign the treatments to the treatment. Randomly assign the treatments to the subjects or randomly assign the subjects to the treatment groups. Okay? So that's how you do the liner. And I think we're going to do a nice long example here next, so let's stop this video.